All right, so at this point we've talked about the fundamental counting principle, we've talked about what a factorial is, we've talked about what a permutation is, and we talked about how to get the factorial and permutations in your calculator. So let's take a look at a couple of examples applying the formula and just getting comfortable with the calculator going and calculating various things. So for number 4, it says a baseball team has 9 players. Find the number of ways the manager can arrange the batting order. All right, so originally we would say that we could use the fundamental counting principle here. We have 9 players, so we could do 9 spots, and then every spot you just drop down by 1. But another way to think about this problem is that order matters and repetition is not allowed. So because of that, if we can think about that being a permutation, so my value for n, how many things do I have to choose from, would be 9 items to choose from, 9 players, and then how many of them do I want to arrange? That will be my value for r, and I actually want to arrange all 9 of them. Alright, so that would be the kind of symbolic notation for that, and then at this point in time we could just plop that in our calculator and have our calculator evaluate it for us. But let's tie this back to the formula. So as a reminder, the formula for a permutation of n objects where you're going to choose r of them, that was n factorial over n minus r factorial. And you should know how to use the formula if you were asked to show the calculation by hand, how to kind of tie everything in here together. So my first number goes as a factorial in my numerator. My denominator will be, I will subtract these two and then apply the factorial to their difference. Alright, so then upstairs, I'm going to clean that up just a little bit. My pen is not being cooperative here. Alright, so upstairs I still have 9 factorial, but downstairs 9 minus 9 is 0. So 0 factorial is defined as being 1. Okay. So this really simplifies to just doing 9 factorial. Alright, and then that kind of connects to how the fundamental counting principle says to approach this problem. So it says 9 times 8 times 7 times 6, all the way to 1. Okay, so you have a couple options for how to enter that into your calculator. Once I see that I'm just going to do 9 factorial, it's just a little bit of less button presses for me to select that one. So I'm going to go to my calculator. There's the work from what we did previously, so I'm just going to do 9 factorial. 9, go to the probability menu, grab my factorial, and hit enter. Alright, so 362,880 ways to arrange them. Alright, next example. A radio DJ can play 8 records in a 30-minute segment of her show. So for this particular 30-minute segment, she has 12 records from which to select. How many ways can she arrange her show for that particular segment? Alright, so when she is selecting her records, she has to decide who she wants to play first and second and so on and so forth. So order matters, and she's not going to play a song twice, which we know if we listen to the radio, they do that all day, is they play the same song over and over again. But she's not going to do it. She's going to play different songs for her 30-minute segment. So, how many items does she have to pick from, as opposed to how many of them does she actually get to choose for her set? So she has 12 records to pick from, and she's got to select 8 of them. Okay, so then that fills the spots for N and R. So now at this point in time, let's go ahead and tie this into the formula. So if this is all we needed, and you weren't told to show any additional work or using the permutation formula, you could just plop that in your calculator and get what that number is. Otherwise, I'm going to kind of pull this through so we can kind of see some connections here. So this is going to be up in the numerator 12 factorial. In the denominator will be 12 minus 8 factorial, which simplifies to 4 factorial. Now, at this point in time, if we kind of expand this out, upstairs would be the multiplication of 12 down to 1. So this will be 6, 5, 4, 3, 2, 1. Downstairs be 4, 3, 2, 1. We're going to get some nice simplifying down here on the tail end. So this would be the multiplication, which if you were just to approach this using the fundamental counting principle, and by the way, all permutation problems can be approached using the fundamental counting principle. All right, it's two different ways of thinking about the problem, but this would be then, if she can play 8 records, you would be putting down 8 blanks, 1, 2, 3, 4, 5, 6, 7, 8. There's 12 records for the first spot, 11 for the second, 10 for the third, and so on and so forth. When you're doing a counting principle problem and you see that the count keeps dropping by 1 every time, that's a permutation. Now, fundamental counting principle problems, there are other ones that are not permutations. Like, for instance, we did the one with the password where we allow for repetitions of letters. That would not be a permutation. Permutations do not allow for repetition. So, but it's just a different way of thinking about the problem. So in any case, I'm going to key this part into my calculator just to remind you about how to do that. So first you key in what you want your value for n to be. So then I'm going to grab my permutation function in my calculator, and then the size of your set then. So we want 8 songs. Alright, so then what's it going to be? 19,958,400. So, quite a few different ways for her to arrange her radio show. Alright, for the next one, if 8 horses are entered in a race, and there can be no ties, how many different ways can they finish? Alright, so for the horses, it's going to matter who is first, it's going to matter who is second, and so on and so forth. And it says they finish, so that's all 8 horses, right? So this isn't going to just be like the top 3 spots or anything like that. We want all the horses to finish and there are no ties. So out of the 8 horses, we want to create an ordered set of all 8 of them. So this is going to be very similar to what happened with this baseball team. Anytime that you have a set that you want to arrange all of them, that is going to be equivalent to just doing the factorial of the number. Because the denominator is going to boil down to 0, so you're just going to be left with the numerator. So 8 factorial, let's go ahead and compute that. So 8 factorial so 40,320 ways for the horses to finish this race. Okay, maybe just a couple more examples about doing these permutations. So given a class of 11 girls and 10 boys, how many ways can they line up? Alright, so that's going to be all of them, and they're going to be in one long line. So, you know, there's going to be a leader, the first person, and then there's going to be a person at the end of the line. So order is going to matter when they go to line up. So at this point in time, we aren't caring about the gender, we just want them to line up. So there are 21 people total. So I have 21 people, and I want to create a ordered set where I want to line all of them up. So that's going to be equivalent to 21 factorial. Okay, so 21 people in the first, or could be in the first spot, then 20 people in the second spot, all the way down to 1. So how big is 21 factorial? 21 factorial. Alright, that's scientific notation. That is a huge number. So let's maybe just pull off this up to maybe 2 decimal places, and then we'll have the scientific notation part out here. So this is going to be 5.11 and then times 10 to the 19th power. All right, so this is going to be an approximation. 5.11 times 10 to the 19th power. That means I would move this decimal point 19 spots to the right before I got to the end of that number. Okay, that is a lot of ways to line these kids up. Okay, so we'll just leave that in the scientific notation format. out to maybe 2 decimal places for the significant digits here. Okay, so keep in mind when you see this little e out here, this is scientific notation for your calculator. And depending on what type of calculator you have, it might have a slightly different way of notating the scientific notation, but you definitely want to catch this out here. Don't be so distracted by the front of the number that you don't look all the way out here. So for the next one, how many ways can they line up if they must alternate girl, boy, etc.? So in this one, just to maybe help me figure out the setup, I'm going to put down some blanks. So alright, so I'm lining up the kids. The first spot has to be a girl, and then the second spot a boy. Then I'm going to alternate them. And I don't want to do this for all 21 spots. What we're hoping here is we can see enough of a pattern so that way we can kind of see how to set up the computation. So for the girls, there are 11 girls that could be in that front spot. And then once I fill that spot, there is going to be 10 girls that could be in the next spot, and then 9 in the next spot, 8 in that next spot, and so on and down to 1. Right? For the boys, this boy right here, this spot, there are 10 boys that I could put there to fill in between those 2 girls. Then there would be 9 boys in that spot, 8 boys in that spot, 7 boys in that spot, and again all the way down to 1. Now at this point in time, I still don't want to key this into my calculator manually, right? That would be, I'd have to key in 21 numbers, and there's a lot of room for error trying to key all that stuff in. So here's where we're going to use some of the properties of the computation of multiplication. So the commutative property says you can rearrange the numbers in a multiplication problem, and that doesn't change the multiplication. So it's why, 3 times 5 is the same thing as 5 times 3. So we're just going to do some very creative rearrangement here. I'm going to pull out all the girl numbers here. So the girl numbers, that would be the 11, 10, 9, 8, and then there would be a 7, 6, 5, 4, 3, 2, 1 somewhere down here, right? So all the girl numbers, there would be 11 factorial. That would account for all the ways to arrange the girls. Now, for all the ways to arrange the boys, that pulls out the 10, the 9, the 8, the 7, all the way to the 1. So if I kind of squish all of those numbers together, that would be 10 factorial. So this is the computation I want to do in my calculator. 11 factorial times 10 factorial. Now you have to be very careful on factorials. You can't just combine those. It's a very specialized operation what's going on. So I am going to just enter this on my calculator really how I'm seeing this here, which is going to be 11 factorial times 10 factorial. The other way that you could do this one, remember 11 factorial is the permutation of 11 objects where you're going to choose all 11. 10 factorial is the permutation of 10 objects where you're going to choose all 10, and then you would multiply those calculations as well. It's a different way of keying it into your calculator. In my opinion, it's a little bit longer. There's a lot more button presses there, so I'm just going to key it in as 11. And then I'm going to grab my factorial. And then some calculators may require you to put that multiplication symbol in. I do not believe this one will require me to, so I'm going to do times 10. The multiplication is implied there. Hit enter. Alright, still scientific notation. This is still a pretty big number. So it's going to be 1.45 if I round to 2 decimal places for the significant digits. And then 1.45 times 10 to the 14th power. And we'll do approximately equal because we're rounding a little bit here. So times 10 to the 14th power. Okay, so this one required us to be able to visualize what was happening with the lineup in terms of our positioning. So we did kind of go back to the fundamental counting principle for a little bit until we could start seeing a pattern, and we used our more sophisticated factorials and permutations to enter this whole thing in our calculator.